In previous videos, we developed the constant velocity particle model of motion. It's a good model for making predictions about the motions of lots of objects. We have 3 graphical tools and 1 algebraic one for modeling motion. Of course, we knew, even as we were building the CVPM model, that it had some limitations. In this video, we're going to start developing a model that can accommodate more kinds of motion. And we're going to begin by taking a look at velocity versus time graphs. Imagine a small toy car rolling down a ramp. As it rolls, we'll record the position every second. There's our data. A scatter plot of this data shows that a line will probably not be a good model for this relationship. And after studying model building, you probably know what to do to linearize this pattern. And we'll do that in a later video. But for now, let's just see what we can learn from this graph before we linearize it. First of all, even though the velocity is not constant, the average velocity is still the ratio of displacement to time elapsed. So if we draw a line from the beginning point to the ending point, we can find the average velocity over this 6-second interval. The position changed by 90 centimeters in 6 seconds, so that's 15 centimeters every second as an average velocity. If we zero in on the first 2 seconds, we can see that the average velocity there is lower than the average velocity over the whole time. The position change was 10 centimeters over the 2 seconds, and so that's a speed of 5 centimeters per second, compared with the velocity of 15 centimeters per second overall. If we look at the last 2 seconds, from second 4 to 6, there's a change of 50 centimeters in that 2 seconds, and so that comes out to 45 centimeters per second, and that's larger than the higher average velocity over the whole time. But if we take a look at the middle 2 seconds, from 2 seconds to 4 seconds, what we find is that the velocity that we get is the same as the average overall velocity. So 30 centimeters in 2 seconds is the same ratio as 90 centimeters over the whole 6 seconds. Notice that these lines are parallel. If we narrow the time interval to only 1 second wide, but keep it centered on the middle of the motion, on the 3 seconds, so we're looking at the velocity from 2.5 seconds to 3.5 seconds, the position change over the time, over that 1 second, is going to be 15 centimeters in 1 second, which is 15 centimeters per second. So that's the same as for 2 seconds to 4 seconds, and for 0 seconds to 6 seconds. All these lines are parallel. As a matter of fact, we could keep doing that. We could keep narrowing the time interval beyond 1 second, make it narrower and narrower and narrower, and eventually we would get to a time interval that's so small that it's literally just 1 point wide. The line that touches the graph only at that point would be what we call the tangent line. So this is when the gap narrows down, the time gap narrows down to no time at all. The slope of that tangent line is the instantaneous velocity. In other words, the velocity at that instant. So right at 3 seconds, that is the time when we are going the average speed of the whole entire interval. So the main lesson of this is the instantaneous velocity, the actual velocity at an instant in time, is equal to the average velocity when you're halfway through the motion. So now let's use this to gather some information about the instantaneous velocity at a few different points. We'll take 1 second at a time. The average velocity in the interval from 0 to 1 seconds is 2.5 centimeters per second. The position changes by 2.5 centimeters in that first second, so the average velocity is 2.5 centimeters per second. But remember, the instantaneous velocity is equal to the average velocity right at the halfway point. So halfway between 0 seconds and 1 second is 0.5 seconds. So the instantaneous velocity at 0.5 seconds is 2.5 centimeters per second. Let's make that a chart, and we'll just keep building on this chart as we analyze future seconds. So now let's look at 1 second to 2 seconds. What happens here is a change from 2.5 centimeters up to 10 centimeters. That's a 7.5 centimeter change over that second. So the average velocity from 1 second to 2 seconds is 7.5 centimeters per second. But since that's also the instantaneous velocity halfway between 1 and 2 seconds, which is 1.5 seconds, that means at the moment of 1.5 seconds, the velocity is 7.5 centimeters per second. So let's update our chart with this new data. Now let's look at 2 seconds to 3 seconds. The average velocity over this time interval is 12.5 centimeters per second. And because that's the instantaneous velocity halfway between 2 and 3 seconds, at 2.5 seconds, the instantaneous velocity is 12.5 centimeters per second. So we'll add that to our chart. Now if you look at this, you might see a pattern developing that will allow you to predict what we're going to see in the next interval. So this is from 3 seconds to 4 seconds. The position change is 40 centimeters down to 22 centimeters, so that's 17.5 centimeters per second over this time interval, which means halfway through that time interval at 3.5 seconds, the instantaneous velocity is 17.5 centimeters per second. Update the chart. Looks like this pattern is continuing if you notice that pattern. From 4 seconds to 5 seconds, we find that the average velocity is 22.5 centimeters per second, which means that at 4.5 seconds, the instantaneous velocity is 22.5 centimeters per second. Updating our chart. Now we got one more time interval from 5 to 6 seconds. Here the position changes from 62.5 centimeters up to 90. That's a 27.5 centimeter change over that 1 second. So that means at 5.5 seconds, halfway through this time interval, the actual velocity, the instantaneous velocity, will be 27.5 centimeters per second. So now our chart is complete, and what we're going to do with this is make a scatter plot. This has velocity on the vertical axis in centimeters per second and time on the horizontal axis. We can see this is a straight line. If you saw the pattern, you might have predicted that, because it looks like every time we go up a second, the velocity seems to be jumping 5 centimeters per second. So the scatter plot makes it really clear. And when you do a regression analysis, it's even clearer. The R-squared value is super good, which means a line is a pretty good model for this. So if you draw the equation or write the equation for this line, it would be the velocity is equal to that slope, 5 centimeters per second times time. If you take centimeters per second and multiply by the reciprocal of seconds, you get centimeters per square second. So physicists will often shorten this down and say that the unit is centimeters or meters or whatever the distance is, divided by seconds squared or time squared. That slope has a name. We call this acceleration. So you've probably heard of that word before. What acceleration, generally means to people is speeding up, and in this case, that's exactly what's happening. The object is speeding up. That's not always what acceleration means to a physicist, as we'll find out, but it always does mean the slope of the velocity versus time graph. So acceleration, by definition, is the change in velocity divided by the change in time. So here's a general model that we can build from this. If we have a velocity versus time graph, that will be a straight line for this kind of motion that we've investigated here. It starts at some starting velocity, and the equation for this line is the velocity at any time is equal to the starting velocity plus the acceleration, which is the slope of this line, times the time. This model is called the constant acceleration particle model of motion. So let's break down what those words mean. CAPM for short. Constant acceleration means that the acceleration is a straight line. So we're not going to see velocity versus time graphs that have curves in them in constant acceleration particle model of motion. And it's a particle model because, again, we're not taking into consideration all of the kinds of internal movements that could happen in a complicated system like a car or a tractor or a rocket or something like that. We're just treating every object as if it is a single particle. Let's take a little bit of a look at interpreting the velocity versus time graphs for constant acceleration particle model. If we take a look at this graph, we can learn two things about this motion by looking at this graph. The first thing is we know that the object is moving in the forward direction. And the reason we know that is not because the line has a positive slope. It's because the velocity is always above zero at all times. The other thing that we know is that the velocity is diverging from zero. It's getting farther and farther away from the zero line, which means it's getting farther and farther away from having no velocity. So that means it's speeding up. So the upward slope of this being above the zero line means that this is an object that's going forward and speeding up. This is the motion that we saw with the car rolling down the ramp that we just got done interpreting. Here's another example. Now, a lot of people will make the mistake of looking at the slope of this line and saying this is a line, or this is a motion that's going backwards, but it's not. In fact, this is also going forward, just like the last one. And the reason we know that is because the velocity is always greater than zero at all points. However, in this case, velocity is approaching the zero line over time, which means it's getting closer to not having any velocity, which means it is slowing down. One more. Here we have an object that's going in the backwards direction. And the reason we know this is not because of the slope, but because of the fact that all of the velocity points at all times are below the zero line. And velocity is diverging from the zero line, which means that this object is speeding up. So this is something that's going backwards and going faster as it does. So this is a first look at constant acceleration particle model. Will form a basis for a more complete understanding with more kinds of tools for understanding this motion that we'll learn about in future videos.